Somewhere out past the orbit of Jupiter right now, there's a chunk of ice and rock that started forming before our sun even existed, and the James Webb Space Telescope just managed to read its chemistry well enough to prove it. Not estimate it, not guess at it. Prove it with a level of precision nobody expected to get from a single object passing through on its way back out of our solar system forever. Stick around, because I'm going to walk you through exactly what Webb found on Interstellar Comet 3I/Atlas, why the numbers coming back genuinely surprised the researchers involved, and why this one object is already reshaping how scientists think about the history of our entire galaxy. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edges of our solar system. To understand why this discovery matters, you first need to understand what makes an interstellar object different from every other comet astronomers have ever studied. Every comet that regularly passes through our solar system, no matter how far out its orbit takes it, was born here, inside the same cloud of gas and dust that formed our sun and all 8 planets roughly 4.5 billion years ago. Those comets are essentially leftover building material. And while they can tell scientists a great deal about our own solar system's early history, they can't tell us anything about conditions anywhere else in the galaxy, because they never came from anywhere else. An interstellar object is different. It formed around a completely different star, in a completely different region of the galaxy, at a completely different point in cosmic history. And then, through some combination of gravitational nudges over billions of years, it got flung out of its home system entirely and went drifting through the emptiness between stars until, purely by chance, its path happened to carry it through ours. Astronomers have only ever confirmed 3 of these objects passing through our solar system in all of recorded history, out of what researchers suspect must be a constant, largely invisible traffic of similar wanderers passing through our solar neighborhood, undetected simply because our instruments haven't been sensitive enough or watching closely enough to catch them. The first, nicknamed Oumuamua, was spotted in 2017 and turned out to be a strange elongated object that came and went so quickly that researchers barely had time to point their instruments at it before it was gone. The second, called Borisov, arrived in 2019 and behaved more like a familiar comet, complete with a visible tail, giving scientists a slightly longer window to study it. The third arrived on July 1st of 2025, discovered by a network of automated sky-scanning telescopes called the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which is how the object got its official designation, 3I/Atlas, the number 3 marking it as only the third interstellar visitor ever confirmed. What made 3I/Atlas especially exciting from the moment it was discovered wasn't just its rarity, it was the timing. Unlike its 2 predecessors, astronomers caught this one early enough in its approach to actually plan a coordinated observation campaign, pointing some of the most powerful telescopes on and off the planet at it while it was still active and outgassing, rather than scrambling to study it after the fact from a handful of rushed images. That included the Hubble Space Telescope, which captured detailed images of the comet's dusty coma and helped scientists narrow down the size of its solid nucleus, along with NASA's newer SPHERE-X mission and the James Webb Space Telescope, which is where the story really gets interesting. Hubble's imaging work turned out to be useful in its own right. By carefully subtracting a modeled version of the surrounding coma from its images, researchers were able to isolate the faint signal of the comet's actual solid nucleus underneath all that surrounding gas and dust. Observations from August of 2025 placed the upper limit on the nucleus diameter at roughly 3.5 miles across, though the true size could be considerably smaller, possibly as little as a few hundred yards, depending on how reflective the surface actually is. Ground-based telescopes added their own piece of the puzzle too, with multiple independent observatories confirming that the comet has a distinctly reddened color and shows only minimal brightness variation as it rotates, a combination of traits broadly consistent with what researchers had already seen in Oumuamua and Borisov, suggesting interstellar objects as a category might share certain surface characteristics, regardless of which star system originally produced them. If you're finding this as fascinating as I did while researching it, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. Webb's first major look at 3I/Atlas came in early August of 2020 using an instrument called the Near-Infrared Spectrograph, which doesn't just take a picture of an object, it breaks apart the light coming from it into individual wavelengths, revealing the precise chemical fingerprint of whatever gases are being released. What researchers found immediately stood out. The comet's coma, the cloud of gas and dust surrounding its icy nucleus, turned out to be unusually rich in carbon dioxide compared to water, with carbon dioxide accounting for roughly 87% of the total gas being released, and water making up only a small fraction of that, alongside a meaningful contribution from carbon monoxide as well. That ratio is unusual. Most comets that form and spend their entire existence inside our own solar system tend to release far more water vapor relative to carbon dioxide when warmed by sunlight. So seeing the numbers flipped so dramatically was an early hint that this object had a very different history than anything born here. Then, in December of 2025, after the comet had made its closest pass by the sun and begun heading back out into deep space, astronomers got an even better opportunity. The close solar pass had freshly warmed the comet's ancient ice, converting it into a bright, active coma that was ideal for detailed spectroscopy. Researchers received special approval to interrupt Webb's already packed observation schedule to turn it toward the departing comet, using a different instrument, this time called MIRI, the mid-infrared instrument, across 2 separate observation windows in mid and late December. What came back was the first detailed mid-infrared chemical fingerprint ever captured from an interstellar object, and it included something researchers hadn't confirmed on this comet before, a clear and robust detection of methane gas mixed in alongside the water, carbon dioxide, and even trace amounts of nickel in the coma. But the finding that's genuinely reshaping how scientists think about this object didn't come from the gas alone. It came from looking at the isotopes hidden inside that gas. And this is the part of the story that's honestly the most remarkable once you understand what it actually means. Isotopes are versions of the same chemical element that carry slightly different weights because they contain different numbers of neutrons in their atomic nucleus. The ratio of lighter to heavier isotopes present in any given comet gets essentially locked in at the moment the comet forms, shaped by the exact temperature, density, and chemical makeup of the cloud of gas and dust it condensed out of. Once that comet is fully formed, its isotope ratios stay largely preserved for billions of years afterward, almost completely unaffected by anything the comet experiences later, even an epic multi-billion-year journey through the emptiness of interstellar space. In other words, isotope ratios work almost like a signature stamped into an object the moment it's born, one that survives essentially unchanged no matter what happens to it afterward. This is precisely why isotope measurements carry so much more scientific weight than simply cataloging which molecules are present in a comet's coma. Knowing that a comet releases water, carbon dioxide, and methane tells researchers what it's made of, but it doesn't by itself tell them when or where that material came together. 2 comets could contain nearly identical mixtures of gas and still have condensed under wildly different conditions, separated by billions of years and thousands of light years. Isotope ratios cut through that ambiguity because they're essentially a physical record of the temperature and density of the specific environment the ice formed in, a record that survives intact regardless of how much time has passed or how far the object has traveled since. That's what allows scientists to look at a comet passing through our solar system today and make a reasonably confident statement about conditions in a star system that may have stopped existing billions of years before Earth itself formed. Using Webb's NIR spec instrument, a research team led by scientist Martin Cordner at NASA's Goddard Space Flight Center measured the ratio of regular hydrogen to deuterium, a heavier version of hydrogen, sometimes called heavy hydrogen, locked inside the water ice on 3I/Atlas. What they found was startling. The comet's water carries roughly 30 times more deuterium than water found in comets that formed inside our own solar system. That level of enrichment only happens under very specific conditions, in an extremely cold environment where ice forms slowly and never gets warmed enough afterward to reprocess that heavy water back down into the more common, lighter form we're used to seeing here. The same team also measured the ratio of carbon-12 to carbon-13 locked into the comet's carbon monoxide and carbon dioxide, and found only trace amounts of the heavier carbon-13 isotope compared to the much more common carbon-12. That matters because galaxies slowly become enriched with heavier isotopes like carbon-13 over time, as successive generations of stars are born, live out their lives, and die, seeding the surrounding gas with heavier elements forged inside them. A young star system, like our own sun, which formed relatively recently, at around 4.5 billion years old, ends up with noticeably more carbon-13 mixed into its material than a star system that formed far earlier in the galaxy's history, before all those generations of stellar enrichment had a chance to build up. Put those 2 isotope signatures together, the extreme deuterium enrichment and the near absence of carbon-13, and the picture that emerges is of an object that formed somewhere extraordinarily cold, extraordinarily early, and extraordinarily far removed from the chemical conditions that shaped our own solar system. Based on those measurements, the research team estimated that 3I/Atlas likely formed somewhere between 10 and 12 billion years ago, back during a period astronomers sometimes call cosmic noon, an era in the universe's history when star formation across the galaxy was running at its most intense pace. For comparison, The universe itself is only about 13.8 billion years old, and our own sun didn't form until roughly 9 billion years after the universe began. This comet, if the age estimate holds up, could be older than the sun itself by several billion years, meaning the icy material now streaming out of it as gas began condensing together long before the star at the center of our own solar system had even ignited. A separate but complementary study, led by astronomer Cyril Aupetom at the University of Edinburgh, using the European Southern Observatory's Very Large Telescope, measured a different set of isotopic signatures in the comet, this time looking at carbon and nitrogen locked inside a cyanide compound present in the coma. That team found carbon isotope ratios consistent with what Webb's data had already suggested, offering independent confirmation from an entirely separate instrument and research group. There's also a competing explanation still being debated, proposed by researcher Romain Majolo and colleagues, suggesting that billions of years of exposure to cosmic radiation during the comet's long journey through interstellar space could have altered some of these surface signatures over time, rather than the ratios purely reflecting the conditions the comet originally formed in. It's a genuinely open scientific question, and researchers studying the data are careful to note that the cosmic ray explanation hasn't been ruled out, even though the formation environment interpretation currently has the stronger body of independent evidence behind it, with 3 separate measurements converging on a similar conclusion. There's a third piece of evidence that lines up with the isotope story in a way that's hard to dismiss as coincidence. Well before the isotope data came back, a separate team of researchers, led by Matthew Hopkins at the University of Oxford, analyzed the exact trajectory 3I/ATLAS was traveling on when it entered our solar system, the specific angle and speed of its incoming path. That trajectory traced back to a part of the Milky Way known as the thick disk, a broader, puffier region surrounding the thinner, flatter disk, where our own sun and most nearby stars reside. Stars in the thick disk tend to be significantly older on average than stars in the thin disk, remnants of an earlier, more chaotic era in the galaxy's formation. Having a purely dynamical trajectory measurement calculated from nothing but the object's speed and direction, independently pointing toward the same ancient thick disk origin that the isotope chemistry was separately suggesting, gives researchers real confidence that they're looking at something genuinely old rather than an unusual but comparatively young object that just happens to have some strange chemistry. It's worth pausing here to explain why any of this actually matters scientifically, beyond simply being a cool fact about one passing object. Every star system in the galaxy forms its own comets and icy bodies out of the same basic ingredients, but the exact proportions and isotope ratios locked into that material depend heavily on when and where that star system happened to form. Studying our own solar system's comets tells us a great deal about the specific conditions present here, 4.5 billion years ago, in this particular corner of the galaxy. But it tells us essentially nothing about what conditions looked like in other systems, at other points in cosmic history, because we've never had a direct physical sample from anywhere else. An interstellar object changes that completely. For the first time with an object like 3I/ATLAS, researchers aren't inferring conditions in a distant ancient star system indirectly through modeling or through light collected from a star billions of light years away. They're holding, in the form of gas, Webb can directly measure, an actual physical sample of material that condensed together in a genuinely different part of the galaxy, under genuinely different conditions, billions of years before our own sun existed. That's an extraordinarily rare kind of data point, one that no telescope pointed at a distant star could ever fully replicate. Because a telescope can observe light from far away, but it can't taste the actual chemistry the way a spacecraft or a direct spectroscopic reading of a passing comet can. None of this comes without real limitations, and researchers involved in the work have been careful to say so publicly. This is a single object, observed during one relatively brief passage through the solar system, and some of the isotope ratios involved, especially the nitrogen measurements, carry fairly wide uncertainty ranges. A conclusion built from one visitor, however compelling, isn't the same as a conclusion built from a large, repeated sample. That's exactly why astronomers are so focused on what comes next. The Vera Rubin Observatory, a new ground-based survey telescope that recently began its full operational survey of the southern sky, is expected to dramatically increase how often interstellar objects get detected, potentially finding several per year instead of once every few years. The rough detection rate that gave us Oumuamua, Borisov, and 3I/ATLAS across nearly a full decade. If that happens, researchers will finally be able to compare isotope signatures and formation histories across multiple interstellar visitors, rather than drawing conclusions from a single ancient wanderer. And that comparison could end up teaching us more about the actual diversity of planetary systems across the galaxy than any single telescope pointed at any single distant star ever could on its own. For now, 3I/Atlas has already passed its closest approach and is heading back out of our solar system, never to return, following a hyperbolic trajectory that will carry it back into interstellar space permanently once it clears the sun's gravitational influence. Every additional observation researchers manage to squeeze in before it fades out of reach adds another piece to a chemical record that took 10 billion years to write and that we only got a few short months to read. It's worth mentioning that scientific interest in this comet hasn't been limited to chemistry alone. Given how rare confirmed interstellar objects are, some researchers use the opportunity to also check for anything unusual in the radio spectrum, just in case. In mid-December of 2025, the Breakthrough Listen program pointed the Green Bank Telescope in West Virginia, one of the largest steerable radio telescopes on the planet, directly at 3I/Atlas during its closest approach to Earth, scanning across a wide range of radio frequencies for any signal that might indicate artificial origin. The search came back with a clean, straightforward result. No candidate signals of any kind, consistent with every other line of evidence pointing toward exactly what the chemistry data already suggested. This is an ancient, entirely natural comet, not an artificial object of any kind. Its unusual chemistry, the product of billions of years of natural formation in a genuinely different corner of the galaxy, rather than anything manufactured. So, what does all of this actually add up to? A piece of ice that began forming before our sun existed, drifting through the emptiness between stars for billions of years, happened to pass close enough to Earth for the most powerful telescope humanity has ever built to catch its chemical signature on the way through, and what came back wasn't just confirmation that the object was old. It was direct physical proof of what conditions looked like somewhere else in the galaxy. At a point in cosmic history none of us could otherwise ever hope to sample directly, delivered not through inference or modeling, but through an actual piece of that ancient world passing close enough for our instruments to finally take a real, direct look. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance the next interstellar visitor is already on its way in, and Webb will be ready and waiting when it arrives. Thanks for watching, and I'll see you in the next one.